What I want to talk about is indeed liquid scintillation counting and gamma spectrometry, because you asked to have a look to how to analyze strontium-90 and cesium-137, two specific isotopes, and how to analyze them if you take water or soil sample, how to proceed. This is also what we will show in the labs when you visit the labs in SCKCN. So first of all, I wanted to go over strontium-90. So what is strontium-90? How to do the sample preparation in order to be able to determine this isotope, which analysis technique is used, and then just to show you some results which you should be able to obtain. And then for cesium-137, I would like to go in the same way. So what is in fact the cesium-137 isotope? How to do the sample preparation for in order to be able to determine this isotope? Which analysis technique should we use? And then again, show you some results. So that's more or less the outline of today's course. So first of all, strontium-90. So strontium is in fact a silvery metal. It can turn yellow due to oxidation. So most of the time we see it as a yellow product. Strontium-90 is present due to nuclear testing. It's also used effectively as a fission product in nuclear medicine. So in order to use it for cancer treatments. And it's also found in nuclear waste of reactors. It's in fact a radioisotope with 38 protons and 52 neutrons. So if you still remember from the course on radioactivity, this is in fact an isotope with an excess of neutrons, and therefore it's an easy beta emitter. So it goes from strontium-90 to yttrium-90 with beta emission, because one of the neutrons can go to a proton and emitting then an electron and an antineutrino. So the high level of neutrons gives us a decay, a beta decay, and it goes to yttrium-90 with an energy release of 0.546 milli-electron volts. It doesn't stop there, because yttrium-90 itself is also unstable, and it goes with a half-life of 64 hours towards zirconium-90. Zirconium-90 is a stable isotope. So you have two beta releases before you go into a stable isotope. It are these releases that we will measure. The half-life of this isotope is 29 years, and this means also that, as you still remember from the radioactivity course, if the half-lives are low and within the lifetime of our cells, we have to do decay correction, and this is indeed needed when we measure the strontium-90. You need to mention the time you took the sample, you need to mention when you do sample preparation, and you need also to write down when you did the measurements in order to be able to calculate back to the target dates. So the measurement time is crucial, and it's important to know that down. Do you still remember, because this is now a beta emitter, what we have to do as protection for beta emission? Any ideas?
I'm looking to the chat, Ingrid. I'm already very happy that for so far we can hear and see everything.
Okay. And I hear you back.
yeah, so that's also good. Let's give them a little bit more chance to the question and the translation. How protection needs to be done for beta emitters?
Yep.
So the beta emission goes along with an electron and some energy.
Mm-hmm.
But I think you will have to remind the audience to what protection can be done, Ingrid.
Yeah. So what is crucial for beta emission? Indeed, it goes not so far as gamma. Eh? It's just an electron, but an electron with high energy. But some plastic tools can already help to stop the beta emission. So we use plastic tools indeed to protect ourselves. Of course, we take as much distance as possible, but in fact, some 10 to 20 centimeters is already good enough. For the rest, we do, of course, we use lab coat, we use protections for our hands, because with beta emission, the most important thing is that you don't take it in, that you don't take it home, that it stays in the lab. So that's why you have to protect your clothes. We sometimes also use overshoes, so also to be able not to bring it out of the lab. And then the other protection is, of course, monitoring. We monitor the lab, but we also monitor ourselves. So you will all be, when you are entering our labs, all will be monitored constantly. So highest protection is take some distance, protect yourself with plastic tools, and then protect your clothes and your hands and shoes. So, but you will be guided in our lab that there will be no issue, and we will work with low activity, just to be sure. Okay, so step by step sample preparation. What will we do? So the first thing we have to do, and I will go into detail for every step, but then you have already the overview. We do first sample preparation, and it means we will have to digest, bring it into solution. We use most of the time a microwave digestion system, but anything like a high pressure system that brings your material into solution is okay. This is just an example of a microwave we are using. After that, we have to do radiochemical separation. Maybe you still remember when we have beta emission, the beta emitters have not a specific energy, but a high broad spectrum, and because of that we have to separate all the rest of the nuclides away. So we have to do specific radiochemical separation, and we use therefore a strontium resin. I will go into more detail about that. And then afterwards we will have to do the measurements when everything is in liquid and separated, and we use therefore a liquid scintillation counting. It's a specific detection system for beta emitters. So for the strontium sample preparation, direct measurement is not possible, except just to look for overall presence of radiation. So is there radiation present? Is there gamma, beta, or alpha present? You can measure directly on your soil or water sample. However, if you want to do quantitative analysis, or if you have low amount of beta and alpha emitters, you have to bring it into solution. You cannot measure directly. So bring the sample into solution, dissolve it is the first step. We use specific acids for that. And because of the beta emitter, it's crucial to separate. Just to remember, this is a continuous energy spectrum. As you can see, there is big overlap of all emitters. And also if you have alpha and gamma emitters, it will give you extra energy background, and you will not be able to do quantitative analysis. So separation is crucial. Here are some ways we do according to IAEA sample preparation steps. So they're officially documented how to do those. So we have water samples where we add phosphate, we wait for some hours, and then on the second day we decant, so we put only the residue that is dissolved into 6 molar nitric acid. For soil or sediments, we go via microwave digestion, also with nitric acid, and then we do an evaporation. An example for fresh milk, which is also followed up with strontium-90 contamination. So There we have specific sample preparations. We decant the milk and wash the resin with warm water. Then you have a DOEX resin on a column. You elute with a specific strontium, calcium, and barium into a 4 molar sodium chloride to form, let's say, a calcium, barium, or strontium carbonates. And then you go to separation. So depending on the sample, you have different ways of bringing it into solution. Because we're talking here about soil and sediment, it's, let's say, we go over microwave digestion using nitric acid, and then we evaporate all the solution away. After that, you have then a specific strontium resin column that's used with also specific amount of acids. And then you elute, let's say, all the rest over the column. Afterwards, we add also oxalate acids. And by doing so, we can elute then the strontium only. Yeah? So it's proven that none of the rest will come off, only the strontium will come out of the resin column. And that's then measured. So first step was bringing it into solution. And then the second step is separation. And it's used by it's called an ion exchange column. And for those who like chemistry, so the extractant that's used is drawn there. It's a crown ether molecule. Of course, if you do separation, it's important to follow the yield, because if we do a separation and only part of the strontium is going through, either it's reproducible and we can correct for it, or it's unreproducible, then it's even worse. Huh? So it's of course important that we have a high yield and then it's also reproducible. So how do we follow then? And we do it every time. We follow by mixing already before our separation an activity or a concentration that's well known. Either we use a strontium 85 spike that's well defined, or a natural strontium spike. By doing so, we follow the yield and we know exactly what's coming off. And we know then, okay, our strontium 90 was separated in a normal way, reproducible, and with a high yield. Most of our separation yields that we calculate now is above 90%. So within all errors that are coming together with your analysis, this is seen as very good. But when you start for the first time in your lab, it would be good to always spike before you do the separation. And we still do it, although we always have above 90%. But you never know that something goes wrong in your separation step, and it's of course a very crucial step. So monitoring, we measure then the strontium 85 in the separated fraction with gamma spectrometry, because it's a gamma emitter. Or if we use the natural strontium spike, we measure then the strontium with ICP-MS, just to be sure what the yield is. So that's a very important element for separation. So again, separation steps, it depends also on the contamination and the other nuclides that are present. Sometimes we do an extra removing of nuclides. So for example, if a lot of plutonium is present, we use first a specific column separation by separating the plutonium out of the rest of the diluted fraction. This is just an example. If plutonium is present, we have, let's say, different ways of going forward. But to eliminate the plutonium then from your fraction, we use 2 to 3 milliliter of 9 molar HCl onto a DOEX it's called like that, 1x4 column. That is also preconditioned with the 9 molar HCl. After it's going through, we evaporate to dryness, and then we bring that back into solution. So if you know that plutonium is present, because that's also high beta emitter, we make sure that we first eliminate the plutonium itself. So after that, eliminating extra nuclides or going directly from the microwave digestion, where we brought the sample to dryness, we take 6 molar nitric acid and also 0.01 molar of oxalic acid. We bring the dry material into that solution, and that solution is then brought over a pre-cracked strontium spec column. That's preconditioned also with 6 molar nitric acid. If we've done that, and yeah, the columns you can find on the internet. So we use, for example, the Trischem columns, but there are other manufacturers that also sell those columns. After that's done, we do a washing step. The strontium fraction is then eluted in a fraction of 10 milliliter of demineralized water. So don't worry, we will bring an SOP to make clear that are the different steps to do the separation, because that's, of course, the most important step in between. What else is a challenge if you have to measure strontium-90? Well, one of the challenges is that there is always strontium-89 also present. They're usually present together. They're both products of nuclear fission. So nuclear reactors or nuclear weapons, they deliver you both isotopes. It's produced also in similar quantities in fission reactions. They're both highly radioactive. Strontium-90 goes to yttrium-90. Strontium-89 goes to yttrium-89, both giving beta decay. Good thing is that the strontium-85 has a shorter half-life. So most of the time, the decay is very fast, and the half-life is 50 days. While for strontium-90, it was 29 years. So although they're both present normally, surely if they're fresh produced, most of the time, if you're doing sampling, the strontium-89 is already gone or almost gone. If you do fresh sampling, it's chemically similar. Both are present after separation. There is no way to separate those isotopes. And both are emitting beta radiation, so they're both contributing to the count rate. So if you don't know, then you have to assume that both are present. Of course, you can wait a little bit for decay of the strontium-89, and then the activity will decay much faster, and then you're sure that you only measure the strontium-90, if that's important. There is another problem present, another challenge. So we said already strontium-90 is going to yttrium-90, but yttrium-90 is in fact an in-between isotope, and it's unstable. So while you're measuring, the strontium-90 is still going to yttrium-90, but the yttrium-90 is already going away. So that means that, let's say, during your measurement, your concentration could change. And that's not something that we want to have, of course. We want to have an accurate measurement of the strontium-90. And that's why we always said, like, we need first an equilibrium. Because otherwise we're counting both the parent, the strontium-90, and the daughter yttrium-90 isotopes. So because radioactive decay is a stochastic process, fluctuation in the results will end up if we're not waiting for an equilibrium to happen. So we're always waiting for an equilibrium, allowing the system to stabilize, and that leads to more reliable and reproducible measurements. After 3 weeks, you get an equilibrium, and that's why the strontium-90 determination always takes what we call a month. So you first have to bring your sample into solution. Then you have to have, let's say, a separation step. And after the separation step, we wait 3 weeks to have the equilibrium and not fluctuating results. So if you look into literature, it's called secular equilibrium. meaning that the yttrium-90 is continuously produced while decaying from the strontium-90. So, but we've proven after 3 weeks, and it's also written in literature, after 3 weeks, we get an equilibrium, and then you can have a stable measurement of the strontium-90 concentration. Now, how does liquid scintillation counting works? So that's the analysis technique we use, and it's based on the following facts. If you have a beta particle, it carries kinetic energy, so energy of movement, and through collision with solvent molecules, part of that energy is transferred to the solvent. And you bring that solvent in an excitation state. That excitation energy is then transferred to a specific organic scintillation molecule, for example, a fluor molecule with a lot of electrons present. That molecule can release its excitation energy as a light photon. And those light photons are measured by a photomultiplier, generating an electrical signal, so a current or a voltage. So it's a whole step before you finally can measure the beta energy. So liquid scintillation counting is used for the characterization of specific beta emitters. So all those that deliver, let's say, an emission of electrons, positrons, and of course, always also the antineutrino and the neutrino is emitted. Examples of beta emitters that can be analyzed in this way is tritium, carbon-14, chlorine-36, nickel-63, the strontium-90, and the plutonium-241. There are others, but these are the ones that most of the time are analyzed with beta emission, because for a lot of other nuclides that also give beta emission, there are other ways to characterize in an easier way. Because as I explained, bring it into solution, do all those separation steps, being sure that your separation is good, is a lot of work. So if there are other ways, most of the time we use different analysis techniques. So you see a photo of a liquid scintillation counter and also a schematic overview. In fact, the counter itself is pretty simple in the sense that it's based on light emission from your sample and using a photomultiplier tube to convert the light into an electrical signal. Now, in liquid scintillation counting, how to get that light emission. So as said, we add some molecules, and we call that liquid scintillation counting cocktails. So they're on the market, and they're based, in fact, on organic molecules, the solvents that get in an excited state, and then additives. Additives can be organic double bonds, like the fluor molecule I showed 2 slides ago, or let's say also inorganic material, as long as it emits light after excitation, can be used. And zinc sulfide is also some example that gives you emission of light. So it's in fact converting kinetic energy of beta into light energy with a wavelength that is compatible with a photomultiplier tube. The amount of light related to that, to the amount of energy, it's in fact the amplitude, your concentration. The number of pulses generated per unit of time is related to the intensity of the radioactive source, and it's in fact the frequency or the energy. And the maximum energy is then related towards which isotope you're looking at. So for strontium-90, you have a specific maximum energy. Some remarks still, by adding the cocktail, of course, it's important that the sample and the scintillator material, the cocktail, is mixed as a homogeneous liquid. As you can imagine, if that's not the case, you cannot measure in a reproducible way. So adding the cocktail towards your sample should be mixed in a very homogeneous liquid. Most of the time, that's no problem if you've brought your material into solution in a proper way. Then the cocktails can be mixed very easily in a homogeneous way. Of course, also other issue is avoid quenching. So that's why we do separation of all the other radionuclides. That's essential because otherwise the other beta emitters will also react with your cocktail, giving you light energy, which is then not coming from your strontium-90, but coming from the other nuclides that are present. So these are examples of organic scintillators. So typically aromatic hydrocarbon compounds with alternating single or double carbon bonds containing p orbitals with delocalized electrons. So it's called the conjugated system. They're often used because then the light emission that is based on the energy transition from these delocalized electrons is indeed measurable with the photomultiplier tube. Excitation in this way is very efficient, and the de-excitation, so going to light, is very fast, is in the nanoseconds range, so you can do your measurement in a very fast way. And really in the dark, you can see the samples glowing. This is also the blue glow you can see sometimes if there are pictures taken from a nuclear reactor, you also see that blue glow. These are typical liquid scintillation spectra. There can be produced, of course, in linear or logarithmic scale. So it's always the number of counts detected versus the energy. The linear scale is mostly used for high energy radioisotopes. The logarithmic scale is more suitable for low energy radioisotopes. And as you can see here, for tritium, carbon-14 and chlorine-36, we have specific maximum energies that are typically then for those radionuclides. So how is that spectrum composed? So you have the counts versus the energy. The Emax of the beta decay is in fact randomly divided between the energy of the beta particles measured by the liquid scintillation counting. But as you remember, when we have a beta particle, there is always also an antineutrino. So if we have a positron particle, there is a neutrino. If there is, let's say, an electron, we have the antineutrino. And they are lost for the liquid scintillation detector. It's the beta particle that is measured. The spectral shape of the beta decay is always starting at 0, calling channel 1, and it ends at specific maximum energy. In between, there is a continuum of energy. It's in fact a probability curve. It's not always the same. But it's of course the same in the sense of if you always measure the same amount and the same nuclide, then you get the same spectrum. So the energy distribution is, in fact, distributed over beta particle and the neutrino. So when you look at the first point in the spectrum, in the distribution, most of the energy goes to the neutrino and not to the beta particle. If all energy goes to the beta particle, then we're ending at the energy, the maximum energy. And of course, that distribution is the same for that same nuclide. So as you can see, it's a little bit more difficult than, for example, alpha and gamma spectrometry, because with alpha and gamma spectrometry, we have a specific energy line. And in this case, we have, in fact, a continuum. The counting efficiency for liquid scintillation counting is very high. So it depends a little bit on the radionuclide, and it's also determined on the maximum energy. But because we're doing a calibration with the liquid scintillation counting for that specific nuclide, you know the counting efficiency of your instrument. It's also possible to measure as of a complete geometry, so a 4P geometry turning around, and then you get a counting efficiency of almost up to 100%. You will see when we talk about gamma spectrometry that it's completely different. So there the counting efficiency is much lower. We do internal calibrations. If you do internal calibrations, that's the most safest way. So putting your calibrator into your sample, you avoid issues such as quenching. You have the best calibration that's possible. However, it also produces a lot of waste because you have for every sample an extra sample with your calibrator inside. If you are in fact measuring always the same type of samples, external calibration is more than good enough. You have less waste, and you also have nice reproducible results. Internal calibration is important if you have, let's say, a lot of different kind of samples where you're not sure that your sample preparation was completely okay, that you're not sure that all nuclides are gone. So then internal calibration can help to make sure that the quenching is taken care of. So, but both are possible, and if you know your samples very well, external calibration is working also very good. Now we come to the results. So we had the sample preparation and some explanation about how liquid scintillation counting is working. So we measure according to a specific procedure. It's described also in IAEA procedure. We're using a tricarb from Perkin-Elmer or a Cantulus. That are two instruments we have. And it's in an acclimatized measurement chamber. The most important thing is that it's stable, that the temperature is stable and the moisture and temperature in your chamber is stable. It can be a little bit higher or a little bit lower. That doesn't matter, but it should be more or less stable. When strontium-89 is present, we first measure strontium-89 in the so-called Serenco mode. You can see an example there. So the channel is related to the electron volts, and then the counts is related to the intensity of the strontium-89. What is in fact a Serenco method? Serenco mode is we don't add any cocktail because the hard beta emitter can emit a blue glow itself. So it's emitting, in fact, UV light, and then a cocktail is not needed. And strontium-89 is one of them. So if you think you have to correct for strontium-89, you can first measure your sample in the Serenco mode, where, let's say, strontium-90 is not present. It cannot do this, but strontium-89 is. Of course, the counting efficiency is sensitive to color quenching. If there are other nuclides present that can do the quenching, then you have, let's say, a measurement that's not counting for everything. It depends also on the sample volume and its concentration. So it's important that you know exactly the sample volume. And if you've calibrated, you have to do that with the same amount of sample. Also, the type of the counting vial is crucial. As we said already, beta emission will be stopped with plastic and depending on the thickness of the plastic. So we still need to be able to count for the beta emission and to be able to count for the light that's going out of the vial. So the type of vial you use is also very crucial. So of course we use the same vial then for the sample as for the calibrator. If you've waited long enough or your sample is not fresh, then we normally go directly to the measurement of the strontium-90 because we assume that strontium-89 is not present anymore. But if you're not sure, you can do this measurement. So if we go for strontium-90 measurements, we add a cocktail of 12 milliliters of cocktail to the sample, and we measure then the strontium-90 and yttrium-90. So the sample is measured in the liquid scintillator counter in the high energy mode. You can see on the top the spectrum where we have done, let's say, a measurement directly after separation. So there is not yet an equilibrium. And underneath, you see then the measurement after equilibrium. And as you can see, yeah, the amount of yttrium-90 and strontium-90 is changing over time. So that's why we always say, like, we want to have stable measurement in order to do the correct calculations of the activity. So we go for the second spectrum where both yttrium-90 and strontium-90 can be seen and calculated for. If you want to do then a calculation of the mass activity, these are just some formulas. So the mass activity, massic activity, so the activity per unit mass, is in fact the activity you measured with your liquid scintillation counting, corrected for the density and the volume of the sample. You have to correct for the date you measured. So T1 is the date of measurement, T is the target date, so calculating back. And then you have to correct also for the decay constant, and the decay constant is in fact related to the half-life. So that's how we calculate then from our activity towards the mass activity. When you start from your spectrum, you have your counts. The counts are related to the activity by calibrating internally or externally. Now, something about uncertainty. So the uncertainty budget is depending on different steps, of course on the counting statistics itself, but also on the yield, the chemical recovery, on the counting efficiency of your liquid scintillation mode. If you have to correct also for strontium-89, it's also depending on the counting efficiency of the Serenkov mode. And another thing is, of course, the weighing of your sample. So a combined uncertainty of 5.5% is not abnormal in strontium-90 measurements. We get, depending on the sample, depending on the amount of counts, so depending on the activity, we get a typical standard deviation of between 4 to 8%. In order to get lower uncertainties, we sometimes measure 10 times, not the same sample, but different samples. And then we can lower towards an uncertainty of 1%. You could let the software calculate your uncertainties by adding, let's say, all the different steps. We prefer to do the calculation of the uncertainty for every measurement again. It's also because we're a research institute, our samples are not routinely, so most of them are very different. They can go from very high activity to low activity. They start from different sources, all kind of samples. And so that's why we do calculations for every measurement on the uncertainty. One important thing for your uncertainty calculations, if you're using a strontium-85 spike, it starts with a very low uncertainty. However, strontium-85 is degrading very fast. So if you want to have the lowest uncertainty possible, you have to use very fresh spikes. So that's why we most of the time use natural spiking. It has a little bit, let's say, higher uncertainty, but you can use it for a long time and it stays the same uncertainty. While with the strontium-85 spike, if you have a fresh spike, the uncertainty is very low, but after a month, the uncertainty becomes already higher than your natural spike. Just for strontium-90, some results. So in order to know that we're doing the right job and the right way of measuring the strontium-90 and the strontium-89, we have intercomparison exercises that we do every year. So as you can see, for strontium-89 on the left-hand side and strontium-90 on the right-hand side, determination in different matrices, going from water samples to soil samples to milk to even fuel samples. We do an intercomparison exercise and see that we get into the green zone. So that means that the absolute values are correct, but also our uncertainty determinations are correct, which is also very important. So that's a little bit a summary of strontium-90. It's not an easy isotope, and you need some skills. But as soon as you know the protocol, bringing everything in solution, doing the separations, strontium resins are available on the market. Also, the cocktails are available on the market. The measurement itself on the liquid scintillation counting is easy. That's not the difficult part. The challenge is, in fact, in the sample preparation. So that's about strontium-90. It's maybe good to have a small pause because then we can go to the Cesium-137, which is a completely different isotope.
Okay, thank you, Ingrid. I'm looking if there are any questions in the chat. Maybe meanwhile, just a question. You referred several times to this EAAA standard. I think in all the previous talk, we were more talking about AN ISO standards, GLOSOLAN standards, so harmonized standards. I guess for radiochemistry, it's more than the international agency who has, can you tell a little bit how well harmonized methods are globally considered? For example, this method, are they used also in other countries, I would say? Can you comment on that?
Yeah, so we have, of course, also ISO, etc. But ISO for nuclear, it's more about how to work, let's say, how to do calibrations, etc. Because that's also used. It's independently on if it's nuclear, yes or no. But if you're going to nuclear, then we work internationally with IAEA. Not all methods are described, but some methods are described and they're used over several labs. So, not only in Europe, but also in the US, we have cooperations there. It's most of the time used in a lot of different labs. And that's also why, for example, for strontium-90, the intercomparison tests are most of the time for most labs pretty good because we're using all the same kind of methods. If, of course, let's say it's not defined, you get a lot more distribution. Or labs that are not used to work in this way, they most of the time have, let's say, more problems, surely, with the determination of uncertainties. So yes, you can compare it with ISO standards because it's indeed internationally accepted together.
Yeah. Okay, thank you for elucidating this. I propose indeed, Ingrid, that we have a 5 minutes break. So we see each other at 3 o'clock our time or 4 o'clock Kiev time, and then come back for the next session. Okay.
Yeah.
So see you within 5 minutes.
Okay, great.
Yeah.
So Cesium-137, a completely other isotope. It has a low ionization potential. It's formed as a common fission product of uranium-235. There are also trace quantities present from spontaneous fission of uranium-238. It's present from nuclear reactors and from nuclear weapons. And of course, it's also present in nuclear incidents. And most of the radiation in a nuclear incident is coming from Cesium-137. It's a radioisotope with 55 protons and 82 neutrons. In fact, it has also a high amount of neutrons. And indeed, because of that high level of neutrons, we have a beta decay. However, we will not measure this isotope from its beta decay because of all the sample preparation I explained already, but we can easily measure it from the gamma decay. Because when the Cesium-137 goes to beta decay, it goes to barium-137M, a metastable state, and that barium-137M gives a gamma ray of 0.6617 mega electron volt, and it's that gamma ray that we will measure, and that it's typically coming from the Cesium-137. The half-life is 30 years, so very comparable towards our strontium-90 of 29 years. So also here, you need to do decay correction, and you need to write down when you took the sample, when you did the sample preparation, and when you did the measurement itself. So that's the same as for the strontium-90. However, the protection is again different. And I dare to ask again what protection would be needed for a Cesium-137 while you're knowing now that there are gamma rays coming out. Any ideas?
I opened the chat to see which protection can be done for a gamma rays. What I sure remember was it's not only plastic.
No.
Just give them a couple of seconds, Ingrid.
Yep.
I see lead.
Yes, indeed.
Okay.
Yeah. So indeed, for this, yeah, a paper like for alpha or a plastic like for beta won't work. We really need lead shielding. For the sample itself, we use really lead blocks to put around the sample. If it's too high, and if it's really coming from fission product uranium-235 and uranium-235 still present or uranium-238 still present, then we have to go to hot cells, or at least glove boxes, but most of the time hot cells. However, if you're monitoring soil material, then most of the time you still can work in fume hoods, but we protect ourselves and with lead blocks. Of course, we have, like we do for the beta and alpha, we also have our protection of our clothes, but the clothes will not protect ourselves from the gamma rays because it's going completely through. But again, protecting ourselves that we don't bring it on our clothes and protect your hands, etc. And of course, the monitoring, it stays the same. We have to monitor the gamma rays that's coming from this source. But indeed, extra protection is needed for the Cesium-137. The sample preparation is in fact very simple because you can measure directly on a sample. So you can measure directly qualitative analysis, or to compare samples, you can put just your sample in the gamma detector. It's of course at that moment just a comparison of samples or semi-quantitative result. For direct quantitative results, you have to calibrate for geometry, for the density of your sample, the distance to the detector. So you can do that for solid material, but it becomes more difficult because you have to really add, this is the geometry of my sample, this is the density of my material, this is how I will measure. So you need to know already a lot about your sample in order to have good quantitative results. That's why most of the time we still dissolve the samples, because for water materials, for water samples, we've done a calibration. And as soon as you've done a calibration on your gamma spectrometer, you can measure all samples for a full year. So it makes it much easier. You don't have to calibrate every time again. That's why you can measure directly on the sample, but we still say if we have to go to very precise results, we do dissolve our materials. But separation is not needed. Surely not for cesium-137 because it's most of the time in higher concentrations present and it's high energy radiation. So you don't need to do specific separations. And it's most of the time, giving a high energy spectrum versus all other nuclides. So that's the more easy part. So we use a gamma spectrometry, a gamma spectrometer, as you can see on the picture. The biggest part of that gamma spectrometer is in fact the lead castle, because the gamma spectrometer is completely surrounded by a lead castle so that the gamma rays are not coming out of your detection system. It's typically used for gamma emitters between 10 keV and 2 to 10 mega electron volts, depending on the detector you have. Most of the beta and alpha emitters also have a gamma emission line. So most of our beta and gamma emitters can be also detected with gamma indirectly, not directly from the mother isotope, but most of the time from the daughter isotope. So specific presence of gamma emitters such as cobalt-60, manganese 54, silver 108 M, niobium 94, antimony 125. I just mentioned those because that are the most general ones that need to be quantified if you're quantifying waste material or monitoring environmental materials. You can then have radioactive concentration after doing a calibration, and it's a non-destructive analysis, so you don't have to bring it into solution. It's just good to do it if you really want to have a good quantitative result. But it can be directly on materials, and then it's non-destructive. What we use in our labs is a high-purity germanium detector. There are a lot of other possible gamma detectors, but we use those because they have the highest resolution. And because if you're looking to unknown samples with a lot of different nuclides, then that high resolution can really help you. The pity is that the efficiency is lower, but most of the time, if you count long enough, you have more than enough counts to do the quantitative determination. It's based on a semiconductor material, so we use liquid nitrogen for cryogenic temperatures for the semiconductor. If you don't do that, your background is really too high, so you really have to lower the background down. That's just because of the detector. In fact, the charge created in the detector is related to the gamma energy. So the spectrum is really based on counting statistics. So you measure the counts or the charges that are created in the detector versus the energy. So counts as a function of the position or position the energy then. So an example you can see there, you have really very specific lines that give you really one line at that energy. You can be sure that that's then that isotope. So a completely different spectrum than from liquid scintillation counting for the beta emitters. Just to show you a little bit more in detail how the detector looks like. So you have a detector crystal. In fact, the detector itself is very small, although the complete gamma system looks very big, but it's in fact due to the lead castle and then the liquid nitrogen dewar vat, so the cooling of the system. But the semiconductor itself, so the detector itself, is pretty small. How does a nice spectrum look like? So you can measure with gamma spectrometry several nuclides at the same moment. You can do once a calibration, and then you can measure all those isotopes simultaneously, and do a quantification on the specific isotopes one by one with the same spectrum. So yeah, the Cesium-137 is more or less in the middle. The only pity thing for Cesium-137 is that it only has one gamma line, while for a lot of other isotopes you have different lines. And as you will learn during this part of the course, it can help in order to determine if you're really looking to the right isotope, that you have several other lines to check. So again, a little bit about gamma radiation. So it's most of the time coming from an excited state after an alpha or a beta decay. So with the alpha and beta decay, you had changes in the core. With the gamma decay afterwards, it's a loss of excitation energy and there is no changes in the core, so the amount of neutrons and the amount of protons stays exactly the same. It's a very discrete energy, so you have a very nice discrete line, and it's very fast. If the half-life of the daughter nuclide that's coming from the mother, where we start with, the Cesium-137 is in the mother, then that daughter nuclide is called metastable. So mostly the half-life of the daughter is much smaller than the half-life of the mother, and the gamma decay goes very fast. We're in fact not measuring the Cesium-137 itself, but we're measuring in fact the daughter nuclide. But because we know the decays and the half-lives, we can recalculate towards the mother nuclide, the Cesium-137. So, as I explained already, the difficulty does not lie in the sample preparation. You either don't do any sample preparation or you just bring it into solution. That's it. But the difficulty lies in the interpretation of the spectra itself, due to the fact that, the energy line is very specific, but there are different interactions with matter possible. And that's because of the gamma interacting with all that's passing by. So it's passing through a lot of things, giving an interaction with that matter, and that's also seen in the spectra. So ideal, there would be no background and there would be just one peak, but most of the spectra doesn't look like that. So the most important things are, there are a lot of interactions, but I will explain the most important ones, and that's the photoelectric effect, the Compton effect, the pair production, and the pile-up or the sum peaks. The photoelectric effect is in fact an electron absorbance and an X-ray escape. I will explain a little bit more in detail in the next slides. The Compton effect is in fact also an electron absorbance, but delivering a secondary gamma. And then the pair production is an electron absorbance, but resulting in 2 times an energy release. And then the sum peak is in fact gamma rays that going so fast to the detector that they're piled up in the sense and counted as 1. So 2 times the energy counted as 1. I will go in a little bit more detail for the four most important interactions we get when we do gamma spectrometry. So the first one is photoelectric effect. It's in fact an interaction of a gamma ray with a bonded electron. An electron is kicked out of the shell, and the atom comes in an excited state, releasing an X-ray and an Auger electron. In fact, the gamma is then absorbed. So you will count too low energy, you will think that the concentration is lower. So that's in fact indeed a problem, and you have to correct for that. The second one is a quantum scattering. It's an interaction of the gamma with an electron, and a part of the energy goes to that electron, and part stays with the gamma and gives a scattered gamma radiation. So we have in fact not a gamma ray that's gone, but there is some energy loss. And if you look to the spectrum, you don't have, let's say, the red peak, the gamma peak, but you have a whole kind of background. And that energy loss can be a lot, but also much less. So there is, let's say, a whole background in the first part of the spectrum before you see your gamma peak. So it's all before the energy peak of the gamma. It starts from 0 and going up to the gamma peak itself. And then let's say the pair production. Pair production is not so relevant for cesium-137, but for a lot of other isotopes it is. It happens for isotopes that have an energy above 1022 kiloelectron volts. And in fact, it gives an electron on positron formation. So ideally, you would have one peak for all events, but in reality, we call it escape peaks. You have also some peaks, single or double, where you lose the energy, and that's what is called pair production. Again, for cesium-137, it's not relevant, but sometimes if other nuclides would be present and you don't have to separate them away, you will see some peaks that you cannot give, let's say, towards or assign towards a specific isotope. And that can give you some doubts about your spectrum, you see. Some peaks, they're also not so crucial for cesium directly, because cesium-137 only have one peak. So some peaks are those that come simultaneous to a detector with different energies, but fast after each other. So if you only have cesium-137, yeah, it's not possible because you only have one energy. But for a lot of other isotopes, you have different energy peaks, and they can go so fast that they come together at the detector, and then you have a sum of those, of the peak. It's seen as a sum in energy. If, however, there are a lot of other nuclides present and it's high activity, then indeed there can be some peaks. Then it's not some peak of cesium-137 with another some peak of cesium-137, but a peak from another isotope combined with the peak of cesium-137. It gives you an underestimation of your energy of the isotope, so an underestimation of your concentration. And then it gives you also some peaks, which you probably will not be able to assign to a specific isotope. However, for this problem of some peaks, there's an easy solution, because the probability to have a some peak and to have a simultaneous entering at the detector goes very rapidly down with the distance to the detector, as you can see in the graph. So most of the time, if we measuring high active samples, we will always measure it at a distance of 8 centimeters. 8 centimeters is enough to have very low coincidence of some peaks. And then, let's say, you don't have special peaks in your spectrum. But if you see them, then take some distance. and most of the time they will be gone, and then you have a proof that it's even some peak. There is one extra interaction we need to take care of in gamma spectrometry, and that's the interaction with the shielding itself. So as said, gamma interacts in a long distance. We have to shield the detector. We have to shield, let's say, the complete system. But the gamma source, your sample, it doesn't matter. The gamma goes in all directions, and it goes also to the LED shielding, giving you LED X-rays due to photoelectric effects. It gives you quantum scattering of your shielding. So sometimes you get even extra background or some peaks in your spectrum just from your shielding itself. A solution for good detectors is, let's say, that you have different layers. Based on those different layers, the gamma is still interacting with those layers, but you have, let's say, in every layer an absorbance. And you minimize in this way the effect. Because you cannot go doing measurement without shielding. You have to have those shieldings. But new detectors are based on several layers, which minimize this scattering effect. Just be aware that if you're looking to a gamma spectrum, that sometimes you see some peaks which you cannot explain, and it could be coming from your shielding itself. So, summary of the influence on an ideal spectrum. You can see two isotopes, two spectra. So normally for cesium-137, we would have a nice peak at 661 kiloelectron volt. But before that peak, we have a lot of continuum background. We have also sometimes some backscattering. So it is on top of a background. For other isotopes, you even have more problems because for aluminum-208, for example, which lies at very or a higher energy, you have also escape peaks, a double escape peak, a single escape peak, pair productions. So there could be a lot of different peaks present, which you maybe cannot explain unless you're looking towards interactions of matter with the gamma rays of the aluminum-208. And you have to correct for them because otherwise your concentration or activity calculation is not completely correct. For gamma spectrometry, in order to determine in a quantitative way, as said already, you can measure directly for samples, also on solid samples, but you have to use specific holders. The best way is also to use the same holders for calibration as for your sample. If you have low activity present, for example, in environmental samples, or if you want to take reference samples from your environment, it could be a solution to put, let's say, a specific holder, as you can see in the photo, around your detector, because gamma is going in all directions. So, in fact, your detector is then inside your sample, and you can measure very, very low activities. The other important element in gamma spectrometry is the distance. So, always put your sample and your calibrated material at the same distance, and put the complete sample in the same distance. So don't put it directly on your detector. It will damage your detector, not in a physical way, because the detector itself has also a protection, but it will damage your detector because it's too close. And if you have higher activity, the semiconductor will degrade fast. So we always put some distance. So distance is important to protect your detector. Distance is also important to have the right quantitative results. And this is important to minimize the effect of some peaks. So the best way is indeed to have a certain reference plane for putting your sample in. Now, I talked already a little bit about calibration and in importance of calibration. I first want to explain a little bit about efficiency. Because with liquid scintillation counting and the strontium 90 measurement, efficiency is not so crucial because it's very high. If you do a calibration, that's fine, it's corrected for. But with gamma spectrometry, there is a lot of differences depending on which nuclide you're measuring. So depending on the energy zone. So in the graph, you can see the efficiency versus the energy. So in the beginning, the efficiency is very low. For example, in the region of americium 241, you have low efficiency in the low energy zone. It goes up, but at a certain moment, it goes down again. So because if we go to higher energies, those gamma rays go through the detector. So not all gammas are really detected. And that's why you have what we call an energy curve. You have to do a calibration for the energy curve for your detector. Of course, you have to do it only once, but you have to do it. So what do we mean with efficiency? So efficiency is in fact the number of what we detected versus the number of emitted. And the number of emitted is related to the activity of the sample, the probability of the emission, and the acquisition time. Because if you count longer, you also have more emission. So that's what we mean with efficiency. And efficiency depends on the detector you're using, but also on the energy zone you're into. So for gamma spectrometry, you have in fact three kind of calibrations. You have to do your energy calibration, that's your identification. You have to do your peak shape calibration. That's important to have optimal analysis of the area you're looking for in your peak, surely because we have a special background. And then you have the efficiency calibration. That's in fact calibrating your detector. So if we look to energy calibration, identification, in fact, of your channel, so you bring a link between your energy and your peak position. So that, of course, you have to do once, and then it's clear. So normally, gamma spectrometers are very stable, but it's important to do that calibration once, so that you know if you're looking to a specific channel, that you know that's the energy of my gamma ray, and that's in fact that isotope. The peak shape calibration is more about the full width and it's and the tail you have. It's important to have a look into, let's say, the shape and the background of your material. Then the efficiency calibration is the detector response for quantitative information. So it's a relation of the peak area and your activity. Because with gamma, the efficiency is in fact very low. You're talking about 0.01%, and not 100% like we had with beta detection. So efficiency calibration is important for quantitative information. And you can see here, let's say the curve I also showed already. It's about lower energies giving low efficiency. It goes up to 0.05%. And then it goes down again because gamma rays can go through all kinds of materials, also through the detector. So it's difficult to capture them. And that's why the efficiency is so low. However, most of the gamma rays are, there are a lot of gamma rays present, even for small amount of material. So most of the time, it's no problem that the efficiency is so low. We can do efficiency calibration with multi-element source, where, let's say, you have different energies. As you could see in the graph here, you have different energies, different nuclides present, and you can then calibrate for your efficiency of your detector. For different instruments, you have different efficiency. You cannot compare one instrument with the other. So even if you have 5 of the same kind of instruments in your lab, they all have to be calibrated. The high performance germanium detector with working with the semiconductor, as said, is very good for resolution, but less in efficiency. However, most of the time, it gives a good response below 1 mega electron volt. You can also use scintillator detectors, but they have a lower resolution, but a higher efficiency. So it's depending on what you want to measure, but most of the time, we use our high performance germanium detectors. There are a lot of calibration sources on the market. Important is that your standard has the same geometry than your sample. The same kind of vials are used. That's why most of the time we prefer, let's say, liquid materials, and that's why we also bring our materials into solution. It's hard to get standards on the market of solid materials. It's very hard, and most of the time you have to calibrate yourself. And that's why we choose most of the time to go over the liquid material. So as said already, calibration sources can be found on the market. You have multi-calibration source, which is pretty good for your efficiency calibration. You have also single sources on the market. For the multi, the uncertainty increases a little bit, while for the single source, you have an uncertainty from 1 to 2%. You can read that on the certificate. Surely buy sources of a certified lab, so a lab that's working under accreditation. You can use other sources, but it increases your uncertainty a lot. Also, what's important is the lifetime of your source. Be aware that you're working with materials that are unstable. So it depends on the half-life of your material, of course, and of course also on the chemical stability. But surely for nuclear materials, be aware that your half-life has an effect on the lifetime of your standard. Further attention points for calibration sources. So you have to do a correction for decay. The time of measurement is important. If you want to have accurate and precise and stable results, we also do cleaning of all recipients. We do also dilutions, because otherwise sometimes you have instabilities present. So it's sometimes important to do some dilutions at a certain level. We always work in a gravimetric way, not just in a volumetric way, but in a gravimetric way. And we're very careful with mixtures, because you didn't do any separations. It could be that if you have, let's say, or you're entering a calibration source into your material, you can get precipitates, and that gives, of course, then inhomogeneous sources. So yeah, as said already, you could work with solid materials, but it's not so easy to get sources on the market for solid metashes. That's not evident. Other attention points for extra influences on results. So I said already, take care of your background radiation. Be aware of possible interferences and material interactions, because the gammas goes through a lot of materials and does an interaction with that material. Be aware of your Compton background, and also be aware of cosmic background. So that's why we use shieldings to be sure that cosmic background radiation is not seen in our spectra. The difference between sample and calibration source is important, so make sure that your calibration source is as close as possible to what your sample is. That means the geometry, the filling position even, so fill it at the same way, at the same position, the recipient you're using, because also that has an influence, the sample position versus your detector, the composition, so if you're not working with diluted liquid material, but concentrated material or even solid, be aware that your density has a big influence. And of course, the homogeneity. The stability of the detector, so we do a calibration every year. For the rest, the detector is pretty stable, but we use control cards. So we measure what we call QCs, so quality controls with every measurement, and we have then control cards to follow up. If we see that there is an out of spec, or if we see, of course, a decline or an increase, then we will redo a calibration. Be aware that it's also important to know that there is an equilibrium between your mother and daughter's nuclide. Now for cesium-137, there is no problem. It's not like with the strontium-90, but it could be. And to calculate, let's say, back to activities and to mass activities, we also use nuclear data of half-lives, and we typically use nucleonica. Or if you're not using that, you can also mention the reference so that everyone can calculate back. I mean, from your calibration, we can calculate back then towards the nuclear data. But we use nucleonica as a source of nuclear data. Just to show you some results. So this is a full spectrum for cesium, where only cesium was present and a small amount of other nuclides, but most of it was cesium. So as you can see, you see the full energy peak of cesium-137 at 661 kiloelectron volt. You have, of course, the Compton background and the Compton edge. Then the background goes down very rapidly. There is some pileup or some peak visible coming probably still from some other nuclide that is present. And then another result is the cesium-137 gamma spectrum for the, this is one where we have a soil sample with all kinds of nuclides. So it's a contaminated soil sample where you can see different nuclides present from lead to bismuth and cesium, but also actinium was still present, or potassium-40 was present. But as you can see, there are very discrete lines. There are also some peaks in between, but you really can do a nice calibration curve with some sources to really determine quantitative results with for cesium-137. And we will show that also in the lab, how to do the calibration and how to interpret these spectra. Then I would like to thank you for your attention. I know it's a lot if you're not in that area. So if there are any extra questions, please feel free to do so.
Okay, thank you, Ingrid, for indeed shedding some light on the gamma spectrometry. It's a very exciting business, I would say. But indeed, you're right. I think a lot of these things need to be seen in practice, especially the calibration, energy calibration of the detector and things like that. So I'm looking at the chat. if there is any question at this point that's coming up.
I don't have a question, just a comment. I feel like when we covered this in school, it was like a paragraph or like a slide at the end of a lecture. So seeing, it was never really covered in depth. So it's nice to see something that's actually more than an aside.
Yeah, when I was making the presentation, I was thinking like, oh my God, but this is a lot of things behind it. You cannot explain just in 5 minutes. That's gamma spectrometry. There is a lot of things when you see to the spectra, how to interpret this data. And we surely can help you with that to have a good start, because it's not so easy. It's easy to measure. Just put it in a detector and wait. But then...
Yeah, I guess part of it too is being North American. I guess it's not as commonly done. I mean, I've done some work with radioactivity and whatnot, but I think because of obviously Chernobyl and Ukrainian situation and the European situation being related to that, it's all rather new material for me.
Okay.
Yeah. Maybe then a question, Ingrid. So you discussed gamma spectrometry, the liquid scintillation. What are the most common other techniques, if any, that you can use for radioactivity measurement?
Yeah, there's also alpha spectrometry. I touched briefly in the radioactivity course, but because that nuclide was not asked for, I didn't go into detail. So that's one. What we also use, and we surely use it sometimes to do calibrations, is mass spectrometry, because then you can specifically measure that mass. So that's also often used. It's of course not measuring then the radiation itself, but it's measuring that specific mass of the isotope. And for example, if you're measuring strontium-90, and you're spiking with a natural spike, so natural abundance, we measure then the isotopes of the natural abundance with mass spectrometry, so that you have an independent check of your yield. And then, because we know the natural abundance, we know what the relation is between the different isotopes, we can correct for it and then reuse it for the strontium-90 measurement itself. So mass spectrometry is also often used. We have 4 instruments for that, and they're really occupied.
No, okay, thank you, Ingrid. I think you're fully right. It's very difficult, but I think you did a really good job to explain within the time frame the 2 methods, and at least as a start, because indeed it needs to be further elaborated. I don't see any more question out of the audience, so I would like first of all to thank you once again, Ingrid, for giving the general session and this practical session as well. And I think in more or less 2 or 3 weeks, the students will come to your laboratory, and then they will see it how it's done in practice. So also I want to say tomorrow we have the last day of the sessions. So in the morning we have a session on the determination of elements with ICP optical emission. And in the afternoon, we have the last session then on the determination of explosive residues. So if everything goes well, I hope to see you back tomorrow at 10 o'clock our time, 11 o'clock your time. And with that, I would like to thank you all once again for attending the sessions, and then see you tomorrow. So thank you.
Thank you. Goodbye.
Goodbye.
Bye.